Use of the chapter 14, notes 2 on linear regression t-intervals. So today we're going to start working again with confidence intervals, but there's a little vocabulary we need to get to first. First thing we're going to look at is something we brought up in our previous class, which is something called standard error. It's also known as standard deviation of the residuals. We had a definition for standard deviation, a typical distance between the individual data points and the mean. And the definition for standard error in this case is very similar. It's still going to be a typical, in this case, amount of variability in the residuals from the observed y values to the line. So in this case, if we're talking about this graph on the right side, these vertical distances that each of these points are to the line, for example, from A straight down or from C straight up, these are what the residuals are. And our standard error is basically typically how far these points are away from the line. We're also going to look at another type of standard error, abbreviated SEB, which stands for the standard error of the slope. B is sort of the variable that we use for slope, and the standard error of the slope is also a typical amount of variability in the sample slopes from experiment to experiment. So is where the S, the standard error, is referring to how far these points are typically away from our least squares regression line. The standard error of the slope is regarding a typical amount of variability in the sample slopes from experiment to experiment. So one time we graph data, we may have a line that looks like this, another time it looks like this, another time it looks like this. So the standard error of the slope is getting at how much the slopes kind of change from experiment to experiment. Now we'll be utilizing both of these variables as we talk about confidence intervals, which we're going to move on to next. We have this example where we have amount of detergent in grams versus the height of soap suds in millimeters. And one of the things that you're asked to do in this problem is part A, which is write an equation of the fitted regression line. You might remember when we have a computer printout that the value underneath the coefficient heading is A, and it's kind of next to the constant. And the value underneath it is b, that's going to be your slope. So when we write our equation, we know it's going to start with y hat equals, the a value is the first value listed, negative 2.679. The b value is the second value underneath it listed, which is 9.5, along with x. When it decides to define any variables in the equation, the variables are these letters here, x and y. The x is obviously referring to the amount of detergent, and the y is referring to this height in millimeters. In part B of this question, it says, note that S is 1.99821. You'll see that value down here in the table. Interpret this value in the context of the study. So what we're going to do is we're going to use our definition that we had earlier, and we're going to plug in a few values into the definition. So 1.99821 is the typical amount of variability in the residuals from the, in this case, the y values are dealing with the observed heights of suds to the line. So we're just going to mention the number, we're going to talk about this entire definition, and we're going to replace y values with what y is in this problem, and y in this problem, based on our graph and what we said earlier, is the height of suds. And then you'll notice directly underneath this, in part C, it says identify and interpret the standard error of the slope. In your equation, the standard error of the slope can be found under the SE column. There's standard error. Slope is your B value. That was 9.500. So the standard error is going to be next to the slope, and that's going to be this value right here. I'll put a little arrow to it. It's this 0.7553 number. It's in the SE column, and it's in the same row as the slope. When we interpret this, we're literally going to use our definition, and we're going to say that 0.7553 is a typical amount of variability in the sample slopes from experiment to experiment. Now that we've reviewed how to read your computer printout, what we're going to do next is talk a little bit about how you set up a linear regression t-interval. The conditions you can find in your book on page 798. I'm going to take you through what those conditions are, and there's actually 4 for this experiment. The first condition is that independent observations have been taken. And what we mean here is that there are no repeated observations on the same individual. When we deal with independent random samples, we're talking about separate random samples. Here we're talking about separate observations and no repeated observations on the same individual. The second condition that needs to be a part of this interval is that the true relationship between x and y is linear. In other words, just by simple inspection, you should notice that the points, for the most part, form more or less a linear pattern. And if you have that, then it's valid to use this type of confidence interval. If you see a curved pattern, however, then it's not exactly the confidence interval that we want to use here. The third condition is that the standard deviation of the response about the line is the same everywhere. So if we have our least squares regression line right here, what we would expect to see is that for the most part, points are more or less kind of equally spaced above and below the line. And regardless of where we are along this line, for the most part, the points are kind of equally spaced out here. What we're trying to avoid is a situation like the following, where maybe on the left side of the line, the points are all relatively close, but as we kind of move down to the right, we notice that the points kind of get farther and farther on average from the line. So if you see a situation where the points almost looks like they kind of diverge into two lines, again, this is not the kind of interval you'd want to use. The fourth condition is that the response varies normally about the regression line. The idea that we're talking about here is that, similar to a bell curve, what we would expect is toward the middle, you're going to see a majority of the points. So just like we see on a normal curve, a majority of the points are close to the center. As you get further away from the center, fewer and fewer points. So most of the points, again, are pretty close to the line, and as you get farther away from the line, fewer and fewer points. What we want to avoid is a situation where we only have a few points that are close to the line, and a majority of the points are farther away from the line. Maybe like a situation kind of like this. Now, it can be kind of challenging to check conditions 2, 3, and 4. So one way that we check these conditions and kind of take care of all three of these things in one step is to draw a residual plot. So to check conditions 2 through 4, what we're going to do is we're going to draw a residual plot. And if we typically see random scatter and not a curved pattern, it usually means that the relationship is linear, the standard deviation of the response about the line is the same everywhere, and that the response varies normally about the regression line. So that's your key, is to draw a residual plot and verify that it shows random scatter. Now, again, to draw a residual plot, a few steps that you need to do. When you enter the points in your calculator, you are going to do your lin-reg step. Make sure you use lin-reg number 8. Secondly, you're going to go to L3, go to second stat, which is your list menu, and down that first list, you're going to notice there's going to be a residual heading. Make sure you choose that. Finally, to graph the residual plot, go back to your stat plot, second y equals, and graph L1 and L3. Make sure that you do zoom stat, and that will give you a nice looking residual plot. So really, when you check the conditions, despite the fact that there's actually 4 conditions to check, once you check the first condition, we're going to do a residual plot, and if you show random scatter on that residual plot, that means your second, third, and fourth conditions are met. So here's kind of our setup using our table and how we'd run a linear regression t-interval. The name of this procedure is officially a linear regression t-interval, or you can also call it a confidence interval for slope. Both ways are appropriate ways of naming this procedure. You do not have to identify the parameter in this case, or the population, so that's kind of nice about this type of confidence interval. For check conditions, again, the first condition, and a lot of times you're going to use the phrase assume here, but we do want to show that independent observations were taken. So in your list, just make sure that you don't have any duplicate numbers listed. Make sure there's no repeated numbers, and that typically means you have independent observations. So it's a pretty easy condition to check. For the second condition, what you're going to do is you're going to make your graph of your residual plot. Now remember, the residual plot will typically have this horizontal line here, and you're going to see points, hopefully more or less random scattered. So this is not a normal probability plot, it's a residual plot, and we're going to call it as such. Don't just call it a graph, specifically name the type of graph. And it's not a normal probability plot, it's a residual plot. Assuming this residual plot shows random scatter, you're going to say this. And if the residual plot shows random scatter, you may assume that the other conditions for inference have been met. So that's what we're going to write here. We're going to say the residual plot shows random scatter, so we may assume the other conditions for inference have been met. And this is addressing the second, third, and fourth conditions we had mentioned earlier. To carry out the procedure, we're estimating what the population slope is. And we had talked the other day about the idea that we have sample data doesn't match the actual population data. Well, to estimate the population slope, we're going to start with our estimate of the sample slope, B, plus or minus T star, so we can utilize our T star program from the past. And it's going to be multiplied by SEB. We talked about this value on the front of your worksheet. SEB refers to the standard error of the slope. And you can find it in your second column, second row, this value here that's next to the slope. And that's all your formula. Just little b plus or minus T star times SEB. In this step as well, you will identify the degrees of freedom. For this type of problem, the degrees of freedom are actually equal to n minus 2, where n is equal to the number of points that you have. So a little different from the past. It's not n minus 1, it's n minus 2. When you interpret the results, it's been a while since we've done a confidence interval, so you might remember that we started with we are blank % confident that. And in this situation, we want to interpret what the population slope is. Now, when we interpreted the slope yesterday, we talked about the population slope is referring to the mean. You're going to introduce what the y variable is here. So the mean, if we were dealing with the last problem, you would say the mean y was equal to height of suds. So the mean height of suds. Then you're going to say whether it increases or decreases. So I'm going to make a little note here, increases, decreases. I'll underline that. By between, we have a confidence interval. So we're going to list the two numbers that made up the confidence interval, blank and blank. For each increase in whatever the x variable is, if we're dealing with the front side of the worksheet, the x variable was amount of detergent. So the mean height of suds increases by between blank and blank for each increase in amount of detergent of 1, and if there's units, we'd want to include what these units are. It's really a pretty short procedure to write. One step for the procedure. The conditions for the most part kind of flow pretty easily. It usually takes a couple minutes to do a residual plot. Then the procedure is pretty easy to knock off. Just make sure you address the degrees of freedom, and then you've got this one sentence interpretation. That's how you set up the linear regression t-interval, and we'll continue to kind of practice this and introduce the linear regression t-test when we hit our next class.